Hello everyone, I am Harsh and today we are going to discuss the 26th problem from CP-31 sheet by TLE Eliminators under the 1100 rating range. So let's quickly move on to the CP-31 sheet. So this is the CP-31 sheet, 1100 rating box is checked and here is a clickable link to your 26th problem. So let's move on to the problem. So the name of the problem is eating candies. So there are n candies put from left to right on a table. The candies are numbered from left to right. So basically the ith candy has weight Wi and Alice and Bob eat candies. Alice can eat any number of candies from the left. She can't skip candies. She eats them in a row. And Bob can eat any number of candies from the right. Again, he can't skip candies. He eats them in a row. Of course, if Alice eat a candy, Bob can't eat it because it is already completed, right? And vice versa is also true. So they want to be fair. The goal is to eat the same total weight of candies. The weight of candies that both of them are eating should be same. So the question is that what is the most number of candies they can eat in total? So basically you need to maximize the total number of candies eaten by both of them such that the weight of candies that they ate are same. So the value of n, that is basically the number of candies, are of the order of 2 into 10 power 5 and the weight of candies is of the order of 10 power 4, and it's given that sum of n over all the test cases does not exceed 2 into 10 power 5. So let's understand what the question actually means. Okay. So in the question, basically they have first of all given you the value n, which is basically the number of candies, and then they have given you the weights of every candies. Okay. So let's understand this with the help of an example. Let's suppose the value of n is 3 as given in the first test case, and the weight of candies is 10, 20 and 10. Okay. Now what Alice is doing? Alice is eating candies from the left. This is what Alice is doing. And what is Bob doing? Bob is eating candies from the right, and both of them are not skipping any candies. So if Bob is eating from the right, then he will eat every candy from the right. And if Alice is eating from the left, she will eat every candy from the left. So now they want to eat candies in such a way that the summation of weight of candies eaten by Alice is equal to summation of weight of candies eaten by Bob. Now if you just simply look up in this particular example, if let's suppose I tell you that Alice eat one candy and Bob eat one candies, then both of them would end up eating the same number of candies. Both of them would end up eating the same weight of candies, that is basically the number of candies that Alice ate was 1 and the total weight was 10. And similarly, the number of candies that Bob ate was 1 and the total weight was 10. Since they are equal, I can say the total number of candies they can eat in together such that the weight of candies eaten by them remains the same is 1 plus 1, that is 2. And you can look, there is no other scenario in which the weight of candies eaten by Alice and the weight of candies eaten by Bob are same, and hence this is the maximum number of candies they can eat in total. And now if you just simply confirm this answer with the answer given, you can see the answer given to the first test case is 2. So this is what the question actually means. I hope the question is clear to each and every one of you. Now once you understand the question, before proceeding with the solution, let's first of all discuss the expected time complexity within which we have to solve this question. So if you look, the value of n over all the test cases does not exceed 2 into 10 power 5. So basically you can consider n of the order of 1e5, right? So you can say that any solution that works in big O of n or big O of n log n, or anything lesser than big O of n like big O of square root of n or big O of log n, something like this will always give you an AC. But if you have a solution that is working in something like big O of n square or anything bigger than big O of n square, like big O of n square log n as well, so this will definitely give you TLE. So you have to design a solution that works within these time constraints, right? So let's see how we can do this. So when you see this question at first, so what you're given n candies and you're given basically the weights of candies, right? up till n candies, right? This is what you are given. Now, you know that Alice is eating some candies from the left and she is not skipping any candies, right? So she will eat either one candy, two candies, something like this will happen. And Bob is eating some candies from the right and even he is not skipping any candies. So just tell me one thing, what the first thing that comes to your mind? If you want to maximize the total number of candies eaten such that the weight of candies remain the same, what's the first thing that comes to your mind? The first thing that comes is that, okay, it's okay that Bob will eat some candy, Alice will eat some candies from the left and Bob will eat some candies from the right. If I can somehow brute force over this, that how many candies will be eaten by Alice or how many candies will be eaten by Bob, then it would be really great, right? So how we can brute force over the solution? So we can assume that, okay, Alice is eating one candy from the left, or she is eating two, or she is eating three, or she is eating four, up till, or she is eating n minus one candies from the left. If she eats n candies from the left, that option is also available, but that's make a common sense that if she is eating n candies from the left, then the sum of weights of candies eaten by Alice will never be equal to the sum of weights of candies eaten by Bob. Since Bob is eating, Bob will end up eating only 0 candies, right? So what are the possibilities we have? The possibilities are that either Alice eat 1 candy from the left, 2 candy from the left, 3 candies from the left, 4 candies from the left, or something like up till n minus 1 candies from the left. If we have any mechanism where this brute force solution works, then we will be all okay, right? Now let's see what we actually require for a particular case. So what I mean for a particular case, so let's suppose you have n candies and I tell you that let's suppose Alice is eating 2 candies from the left. Okay, so now what I want to check that is it possible that Bob eats some candies from the right and the sum of weights of candies is exactly equal to the sum of weights of first 2 candies. This is what I want, right? Is this possible? Is there any mechanism via which we can check this in lesser than big O of n time? Because there is one mechanism that we can definitely imply that we can check this in big O of n time. We will simply run a loop from here up till we reach at this particular point, and if at any point of time our sum of weight of candies become exactly equal to the sum of weights of first 2 candies, we can simply return that, okay, if Bob eats this many number of candies from the right, he will definitely end up having the sum of weights of candies exactly equal to sum of weights of first 2 candies. That is one solution that we have, but that definitely works in big O of n time. So we have to think that is there any mechanism via which we can just check this in lesser than big O of n time, that if Bob eats some candies from the right, then can the sum of weights of candies eaten by Bob be equal to sum of weights of candies eaten by Alice till now? So yes, there is a mechanism. What you can do is you can use suffix sum with map. And let me explain how we can do this. So what you can do is, if you have, let's suppose, n candies. If let's suppose you have n candies, so what you can do is you can just store in your map that till particular index, what was the suffix sum. Like what you can do, you can store that, okay, till index n, what was the suffix sum. Then you can store till index n minus 1, what was the suffix sum. Then you can store till index n minus 2, what was the suffix sum. This is something that you can store. Now, when I tell you that I have eaten 2 candies, that Alice ate 2 candies from the left, okay? Alice ate 2 candies from the left. So just ask yourself, should we keep these suffix sums in your map? The suffix sum till index 2 and suffix sum till index 1. Should we keep these values in our map? No, right? Because if Alice ate 2 candies, if Alice ate, let's suppose, candies with weight W1 and W2 already, then Bob can't eat these candies anymore. In that case, I should not have these suffix sums in our map because it does not make any sense. So what we can do, till we reach this particular point, we can remove these suffix sums from our map, and then with whatever value is remaining in the map, we can check whether the sum of these weights, that is W1 plus W2, exist in our map or not. If it exists, all good. We have a combination where if Bob eats some candies from the right, the sum of total weights of candies will be exactly equal to sum of weight of candies eaten by Alice. And this is how you can actually solve this problem in lesser than big O of n time. And let me take an example via which these things become more clear. So let me take an example from this only. Let's suppose I take this particular example where the weights of candies are 2, 1, 4, 2, 4, 1. 2, 1, 4, 2, 4, 1. So there are 6 candies in total, and these are the weights of candies, right? So initially what I would do is, first of all, in my map, so considering at 0 based indexing, let's suppose this is index 0, this is index 1, this is index 2, 3, 4, 5. So according to each and every index, I will store the suffix sum in my map. So I will construct two things. First of all, a map that will basically store the index for every suffix sum, and I will store a suffix sum vector as well. I will just create this suffix sum vector as well. So this is basically index 0, 1, 2, 3, 4, 5. So if I just populate this quickly, so the first value will be 1, second will be 5, third will be 7, next will be 11, next will be 12, and next will be 14. Just let me quickly check this. 1, 5, 7, 11, 12, and 14. So yeah, this is the suffix sum vector. And in your map, what you have that, okay, for if you want to sum as 1, the index is 5. If you want the sum as 5, the index is 4. If you want the sum as 7, the index is 3. If you want the sum as 11, the index is 2. If you want the sum as 12, the index is 1. And if you want the sum as 14, the index is 0. This is what that is contained in your map, and this is what the suffix sum vector is. Okay. Now let's try to brute force over the solution. So what are the possibilities I have? That the first possibility is that Alice ate 1 candies from the left. Okay. Eating 0 candies from the left does not make any sense, right? So first of all, Alice ate 1 candies from the left. So if this is so, if Alice is eating 1 candies from the left, just tell me, does the suffix sum till index 0 makes any sense? Because will we ever be able to allow Bob to eat first, or basically this 6 candies? Will I ever allow Bob to do so? I will not allow it because Alice is already eating this candy, so this candy can't be eaten by Bob anymore. So what I would do is, till index 0, whatever was the suffix sum, I will simply remove this from my map. Once I do so, now I know if Alice is eating 1 candies from the left, so basically the sum of weights of candies that Alice is eating is 2. And now I will look, do I have 2 in my map? This suffix sum map, do I have 2? And I will see that, okay, the sums I have is 1, 5, 7, 11, and 12. I don't have 2, so I will simply move on. Now what is the next case? The next case is that Alice is eating 2 candies from the left. So what is the sum of weights of candies that Alice is eating? So it gets updated to 3. 2 plus 1 basically 3. And now again the same thing, since Bob can now never eat this candy anymore, so suffix sum till index 1 does not make any sense. So till index 1 the suffix sum was 12, so I will simply remove this input for 12 from my map. So I will simply remove this. And now the sum of weights of candies that Alice is eating is 3. And so now I will look that, do I have the value 3 in my map? The answer is no, I don't have value 3, so I will simply move on. So I simply move on to the next case, where Alice is eating 3 candies from the left. Okay. So next I will look, Alice is eating 3 candies from the left. So the sum of weights of candies that Alice ate gets updated to 3 plus 4, that is 7. And the same case, I will remove the suffix sum till index 2. So till index 2 the suffix sum was 11. So I will simply remove this input for 11 from my map. And once I do so, I will simply look, do I have the sum 7 in my map? And the answer will tell me yes, I have this 7. And what was the index where I had this? The index was 3. So what is the total number of candies that Alice and Bob will eat? So since Alice is standing at index 2, so basically she ate 3 candies since we are considering 0 based indexing. And since the value at index 3 is equal to 7, so suffix sum till index 3 was 7. So the total number of candies that Bob ate was nothing but the size of this vector, that is 6, minus this index 3. Because we had that, okay, till index 3 we had the suffix sum as 7. So basically the total number of candies that Bob ate is nothing but n minus that index, right? So this comes down to 6. So initialized, we will simply initialize our answer to 0, and we can update this answer with the maximum of answer comma this 6. So this answer gets updated to 6. Next we move on to our next case, that Alice is eating 4 candies from the left. Again, by the same logic, we are removing this input for index 3 because this candy can never be eaten by Bob. So now the sum also gets updated to 7 plus 2, that is 9. We will simply look that do we have 9 as in our map? We don't have. We will simply move on to the next case. So this is our next case where Alice is eating 5 candies from the left. So the sum gets updated to 9 plus 4, that is 13. And again, by the same logic, we will remove this input from our map as well. And now we will look, do I have 13 in my map? I don't have, so I will simply continue. So this is how I have explored all the cases, and at the end the answer that I got is 6. So the answer for this particular test case will be 6. So this is the complete logic to this question. We have simply done, we have simply brute forced over the number of candies that will be eaten by Alice, and we have designed a mechanism via which we can check that if Alice is eating some weight of candies from the left, then is there any number of candies that Bob can eat from the right such that the sum of weights of candies become exactly equal. So this was the solution to this problem, and let's quickly see the code for this as well. So this is the code. So first of all, we are taking the number of candies as input, then we take the weight of candies as input. Then we construct a suffix sum vector and a map named index that will basically store that, okay, for every suffix sum, what was the index at which it occurred. So we are simply initializing our sum to 0. We simply go from index n minus 1 till I greater than equals to 0, I minus minus. Sum gets incremented by weight of I. Index for this particular sum is I, and in our suffix sum at this particular index I, we are simply storing this sum. Now what we do, we simply initialize our answer to 0, initialize our prefix sum till 0, because prefix sum will basically tell me the sum of weights of candies that Alice has eaten till now. So now we are simply iterating over all the indices from 0 to n. This can also be changed to n minus 1 because it does not make any sense if Alice is eating n candies from the left, right? So even if Alice is eating n minus 1 candies from the left, that is the last case we can explore. So first of all, when we come to a particular index, we know that suffix sum till that particular index makes no sense because we can never allow Bob to eat that particular candy, right? So from our index map, we are simply erasing the suffix sum that was present till that particular index. Next, we are just updating our prefix sum with weight of I. So we are simply adding this weight of I to our prefix sum. And then we are looking that in our map, do we have an input for this particular prefix sum? So if we find this, that is basically index.find prefix sum is not equal to index.end. In that case, we are simply updating our answer with the max of answer, comma, I plus 1, which is basically the the number of candies that Alice ate, plus the number of candies that Bob ate, which is nothing but n minus the index at which this prefix sum occurred, right? Then at the end, once we are done with this, we are simply printing our answer, and this is the simple code for this solution. Now, if you just compute the time complexity for this, so taking input takes me a time of n. Constructing this prefix sum and then adding the values in the map takes me n log n, because insertion in maps takes your time of log n. Next, for this loop takes me a time of n, and since over there we are erasing values from the map and accessing values from the map, so again it takes me a time of log n. So the time complexity for this is n log n. So, and since n log n is a dominating factor, we can say the time complexity is, we go of n log n. And the space complexity, if you look, So we have constructed vectors for taking inputs. So this takes me a time of n. This again suffix sum vector takes me a time of n, and this map again takes me a time of n, since we are pushing n values inside it. And rest we are not constructing any extra space, so we can say that okay, the space complexity is also big of n. And these are well within the time constraints that we already discussed, so this will definitely give you easy. So I hope all of you understood the solution well. Thank you.